What is energy? Well, one way to answer this question is to list out all of the different forms of energy. So electric, magnetic, mechanical, gravitational, thermal, and explain the meaning of each. We're going to do that later in this video, but I want to start by pointing out what's fundamentally the same about any form of energy. Any form of energy that you talk about, nuclear, chemical, electrical, is going to have two common traits. First, if you analyze the basic physical mechanism of what's going on with any form of energy, it always comes down to you have some form of kinetic energy or potential energy or some mixture of both. So either all kinetic, all potential, or a mixture of both. These are very closely related to one another. And I'll explain how in a second. But it always confused me if I would read something or watch a video on what is energy, and they would list out all the different kinds of energy, solar, magnetic, thermal. They would also include in that list kinetic energy and potential energy. And I don't think that's the right way to present it. Kinetic and potential energy, to me, is the fundamentals of what energy is. The different forms of energy like solar, chemical, electrical, that's just how we classify energy in different circumstances. But like chemical energy, for example, you'll see that defined as a form of potential energy. Same thing with radiation. It's a form of potential energy. Thermal energy. So the temperature of something is proportional to the kinetic energy of the molecules. So that's why I don't think it makes sense to include kinetic and potential energy in the same list as the list of just general energies that we classify in the world around us. Okay, so again, any form of energy, radiation, waves, there's all kinds of different types of energy that are named out there. If you break down the fundamentals of the physics of what's happening with any of those types of energies, it all comes down to you're gonna have some form of kinetic energy, potential energy, or a mixture of both. Okay, so first, what is kinetic energy? Kinetic energy is the energy associated with a mass that's moving. Anything that has mass, so a car, a train, or an electron, a molecule, anything, if it has mass and it's moving, meaning it has a velocity, then it has a kinetic energy. You take 1/2 times the mass times the velocity squared. Okay, now potential energy, as I mentioned, is very closely related to kinetic energy. Potential energy is stored kinetic energy of a mass based on that mass's position relative to something. Stored kinetic energy of a mass based on that mass's position relative to something. Okay, so what does that mean, stored kinetic energy? Well, think about a body of water at the top of a mountain. Imagine it's still, it's not moving. Well, there's no kinetic energy, but because of its position, so its height relative to sea level or relative to, that would be defined, it depends on the application. You can tap into that water supply, open up a passageway, so put in just a little bit of input energy, and then that water is going to naturally flow because of its height. You can just tap into that kinetic energy. So what's the potential energy of this body of water? Well, take the weight of all of the water and multiply it by the height. And again, the height just depends on the application. If you have a town that's not at sea level, but it's, 100 feet below the water, well, then that's the height. It just depends. But this is the potential energy of that body of water. Chemical energy, that's a form of potential energy. So think about if you have some gasoline. Well, the molecules or the atoms, based on their positions relative to one another, have stored kinetic energy. If you apply a little bit of input energy, just a spark, that container of gasoline that's just sitting there dormant, all of a sudden turns into this high-speed accelerating gas. You release the kinetic energy stored in those molecules. Now, the formula for the potential energy in the gasoline, you have to consider the forces that it takes to push those atoms or molecules into position and fix them in position. Now, I mentioned that any form of energy that you talk about has two common traits. This was the first trait, that any form of energy, whenever you analyze the fundamentals of what's happening, it's just some form of kinetic or potential energy or a mixture of both. What's the second trait? Okay, so what are the units of this kinetic energy? 1/2 times mass times velocity squared. Okay, 1/2 has no units. You've got mass, and then velocity squared is length squared per time squared, right? Velocity is length per time. You square that, you get length squared per time squared. We can rearrange this. So mass times length per time squared times length. These are still the same, right? So what is mass times length per time squared? Well, length per time squared, that's acceleration. Think of meters per second squared. Mass, so like kilograms, for example. Kilograms meters per second squared, that's force. F is equal to ma. Kilograms meters per second squared, that's a Newton. But just in general, not just for Newtons, in general, this is the units for force. So we've got a force times a length. What about the potential energy? Well, weight is a force, and h is another length, force times length. No matter what kind of energy you're talking about, any kind of energy, no matter what it is, the units of that energy is force times distance. The units of energy is a force times a distance. Okay, so this is another way of looking at the fundamentals of what energy is. This kinetic potential energy relationship, as far as if you look at the physics of what's happening, but another perspective of looking at what energy is a force times a distance. So it's a force that's acting over a distance. And this force times distance idea, this is most helpful whenever you think about the definition of energy as the capacity to cause change, an ability to make changes happen. Okay, so first of all, energy is, we define energy. Humans have defined energy. Scientists, physicists, engineers, they first define what force is. Isaac Newton defines what force is. It's an ability to accelerate a mass times acceleration. But then we also notice that a very important quantity is when you multiply a force times a distance. We call that energy, and we realize that that's very important. It's kind of abstract because you can't hold a force times distance in your hand. You can't really hold a force in your hand, but you can still kind of conceptualize a force mentally, right? You can push on something, you can apply a force to something, but then it gets more abstract when you think about force times a distance. Okay, if you think about anything in life, anything in nature around you, for anything to happen, for anything to take place, for any change to occur, there needs to be a force applied over a distance. If you want to drive somewhere, if you want to move something, forces need to be applied, but not just a force being applied. That force needs to be applied, and then that force moves. You can push on a wall and apply a force, but if that force doesn't move, you're not really doing anything. So there's no energy output. Yes, your body outputs energy to push on the wall, so the muscles and everything are moving in your body, but just looking at the system of you pushing on the wall, looking at it from that general perspective, you're not making anything happen because that force you're applying isn't moving. But if you pick up a book, pick up a table and move it, now you've made something happen. You've applied a force over a distance. Okay, now even more specifically, it's not just about energy to make things happen, but really power. What is power? Power is energy per unit time. Force times distance divided by time. It's a measure of how fast energy is expended. So if you walk from Los Angeles to New York, you can either walk or fly. So you're gonna walk there or you're gonna fly there. In both scenarios, you've made the same amount of change. You've gotten yourself from Los Angeles to New York. You've put in the same amount of energy. The same amount of energy was needed in both scenarios. In fact, if you did a careful analysis and you did it appropriately, you could add up all of the forces applied over distance from you walking to New York as well as flying, and you're going to get the same total energy needed to make that happen. But there's a difference, right? What's the difference? In the airplane, when you flew in the airplane, that energy was applied significantly faster. So the airplane is more powerful than you walking there. Now, another way that energy is referred to is like when we say we have energy needs as society. So how are we going to fulfill our energy needs? Well, before I explain what this means, we need to go over a few things. So first, any energy, any form of energy, we talked about how in general it's just some makeup of kinetic and potential energy or some combination of that. But also, any type of energy is either going to be in an organized form or an unorganized form. So the unorganized form, we're talking about thermal energy, heat, temperature. When you measure the temperature of a solid, liquid, or gas body, what the temperature represents is the kinetic energy, that energy of motion, whether rotational, translational, the kinetic energy of motion of the atoms and molecules. That's what thermal energy is. Heat is associated with thermal energy. Heat is the transfer of thermal energy from one body to another, or from one region of a body to another region of a body. However, this motion is not organized. It's completely random, right? The directions that the molecules or atoms are moving is completely random. They're not moving in the same direction. It's unorganized. And just to make it clear, there's no other form of unorganized energy outside of like thermal energy, heat, temperature. And also to make it clear, thermal energy is strictly referring to the kinetic energy of the atoms or molecules of a body. But you can also think about unorganized potential energy, and this will be in the form of chemical energy, chemical potential energy. But this doesn't mean that all chemical energy is an unorganized form of energy. It just depends on the context, the perspective you're looking at it from. A container of gasoline, if you're thinking about burning that gasoline, well, then in that case, that chemical potential energy is an unorganized form. However, when you think about a lot of biological systems, things that take place in cells, etc., the chemical energy contained in bonds is not utilized from the standpoint of the randomness of the kinetic energy. You know, one molecule at a time, a piece of a molecule could be broken off, and that kinetic energy, when it breaks off, is used to attach that piece to something else. So in that context, it's not that's not heat transfer. You're not transferring that random kinetic energy of motion of a unit of molecules to other molecules. But like, for example, in a piston, a piston cylinder in a car engine, you're utilizing the unorganized potential energy contained within the gasoline. So the gasoline vapor is inside of the chamber. You spark it. All of that unorganized, random motion kinetic energy is released. A lot of it gets transferred to all of the walls around it, and even the piston face, just as thermal energy. It just increases the kinetic energy of the molecules of the surfaces around it. Just heats everything up. However, statistically what happens is there are a large number of the resulting gas molecules that are powerfully slamming into the piston face. Not in unison, not at the same time, not in an organized way, but there's still the pressure. There's a lot of powerful force, a powerful overall force being exerted on the piston face. But there's nothing pushing back on the opposite side, so you get this net force on the piston face. That's how you can harness the power of this unorganized energy. A solar panel, light energy or radiation is hitting the solar panel. This energy is transferred to electrons, causing those electrons to jump into these passageways, which create an electric current. But that light energy is not organized. It's just coming in all over the place. It's completely random. It's heating up the solar panels. Okay, now we're not going to talk about the first law of thermodynamics in this video, but you might have heard the term internal energy. What is internal energy? Internal energy is referring to, so if you have a solid, liquid, or gas body, its internal energy is all of the chemical and potential energy contained within the molecules of that body. The molecules are atoms. So it's all of the thermal energy as well as all of the potential energy, so all of the chemical potential energy. Okay, so internal energy is all of the thermal energy and all of the chemical potential energy of a solid, liquid, or gas body. Does that mean that internal energy is an unorganized form of energy? Not necessarily. It depends on the perspective you're looking at it. Yes, from the thermal energy standpoint, it is, but you can't say that chemical potential energy is always unorganized. It just depends on the system. Okay, so that's the unorganized form of energy. What about the organized form? The organized form, you think about the kinetic energy of the molecules or atoms of a solid, liquid, or gas body. They're moving together as a unit. Okay, we looked at this piston cylinder. The piston as a solid metal body, when it moves, all the molecules move together in one direction. That's an organized form of energy. The solar panel, when the electrons get in to the chambers and the current starts to flow, those electrons are moving together as a unit. That's an organized form of that kinetic energy. A flowing river, all of the molecules are moving together as a unit. Now, if you think about it, the river, the water in the river also has an internal energy, right? It has a temperature. There's thermal energy, but it also has that organized form of energy as well. There's like two different systems going on at once. Okay, but then you also think about that organized form of potential energy. We talked about a lake at the top of a mountain. That's stored, organized kinetic energy. Okay, now talking about our energy needs in society. We're trying to harness and obtain this organized form of energy. It's this organized form of energy that we can use to do things in society. So you might be asking, well, what do you mean? What are we going to do with a flowing river? What do we really do with a flowing electrons? Okay, well, remember, any device you see, any machine you see in life, a vehicle, a crane, power equipment, it all starts with a simple form of this organized energy, like a rotating shaft, for example. A lot of machines at the very start are just a powerfully rotating shaft. Think about a car. And what machine designers do is they convert that powerful organized energy into a form of energy that machine can use. Like a car, it converts it into that linear energy, right? That's what machine designers are doing. They're designing machines that can perform functions that we need. But it all starts with some very basic form of organized energy, like a rotating shaft or a piston in a cylinder. So like a linear actuator, like a door sliding open. That's not a rotating shaft. It's something that's being pulled. Like you can imagine, these pistons here don't have to be attached to be rotating a shaft. Maybe they're just pushing and pulling on something linearly. You can create rotating shafts or linear actuators with electricity, with gasoline. So electricity, electric motors, that's what magnetism does. You have these coils, these configuration of these magnetic coils that when you pass current through them, it spins a shaft powerfully. So electricity, we can spin shafts. We use electricity to get light, also for heating. Electrical devices, cell phones, they operate off of that organized form of electrical energy, not the random motion of electrons bouncing everywhere, not the thermal energy, but that organized electric current flow. A flowing river, for example, or like even a wind farm, all that's happening is that organized kinetic energy is being used to powerfully rotate shafts. That's what these turbines are. The water's coming in. This is in the Hoover Dam. The water's coming in and just powerfully rotating shafts. That's what electric generators do. That's how magnetism works. If you can have a shaft rotating, you can create powerful current. That current then gets transferred to homes or even higher forms of voltage, go to industrial plants, go to machine shops. That's what powers saws and welding machines. You can have portable electricity, like you can use batteries, but the electricity coming in from the power lines, that charges batteries. But then there's portable power like gasoline. Okay, now the last thing to talk about before we go through the list of the different types of energies is, so if we've got some system, this is like a 3D system here, this like volume here. So we're not going to get into the first law in detail in this video, but the first law is just a statement of the energy balance. The first law says that energy is conserved. You can't create or destroy energy. So for any system, there's always going to be a balance of energy. It's kind of like an accounting book. You can always track all the money that came in and went out, and the money that was built up or lost in the system. You don't create or destroy money. You can always account for all of where all of the money is and where it went. Same thing with energy. And so in general, what you say for the first law is that the change in internal energy within the system is equal to the heat transferred plus the work done. And again, I'm not going to get into sign conventions. We're not talking about the first law in great detail. I'm just trying to give you a general overview of the energy terms here. Okay, so on the left, it's talking about the energy content within the system, the change in the energy content within the system. So if we want to write out the first law in the most general form possible, the internal energy can change, but also you can have the kinetic energy. Like, okay, you could have a body, a solid, liquid, or gas body that has internal energy, but also that body could have a kinetic energy, and that organized form of kinetic energy or potential energy. So the changes in kinetic energy and potential energy, the organized forms, because remember, the internal energy is talking about the kinetic and potential energy of the molecules, of the atoms. So yeah, you can think about it as the unorganized form of kinetic and potential energy. You can think about it that way, but as mentioned, it depends on how you look at it. But this is the kinetic and potential energies of like bodies as a whole. The internal energy of something within this system may not change, but if all of a sudden it starts moving really fast, then the kinetic energy has changed. So here we're representing all of the energies of what's inside the system. Internal energy, that organized kinetic energy, and organized potential energy of like the bodies as a whole. How can that energy change? Well, we need to have energy transferred across the boundaries, right? You need to, for the energy inside the system to change, you need to have energies transferred. That's what's on the right here. There's only one of two ways energy can be transferred. Well, actually three ways, but okay, the third way is based on mass. Based on, like, so yeah, you can have mass coming crossing the boundary. So that's one way energy can be transferred. The mass would bring in, there's more internal energy the mass brings in, or potentially more kinetic or potential energy, right? But outside of mass coming in and out, there's only one of two ways energy can be transferred across the boundary of a system. There's only two ways, either in the organized form or the unorganized form. If it's being transferred in the unorganized form, either into or out, that's what heat is. That's heat. If it's being transferred in an organized form, that's what's called work. There's only really one form of heat transfer. You know, you're just transferring thermal energy. But there's different forms of work. So like the piston cylinder idea. If you think about the system is the gas inside the piston, well, if it's being pushed on or compressed or expanded, and that piston is moving, that's like a mechanical work being done. But you can also think about the idea of electrical work, magnetic work. There's also the idea of surface energy we're going to talk about in a second. So there's surface work. Any organized form of energy transfer, that's work being done. Okay, so now that we have an understanding of what energy is, let's go through some of the main types of energy. I'm not going to be able to list the name for every single type of energy that you might come across, because these are just random names that people assign based on the circumstance. For example, energy from the sun, someone might call that solar energy. Someone might call that radiation. Okay, but I picked out all of the forms of energy that will give you a full scope of the types of energy that are in the physical world around you. Okay, first, mechanical energy. This is what you can think about as the main type of energy that we as humans are trying to acquire. This is the type of energy that we use. This is kinetic and potential energy, the organized kinetic and potential energy, the organized form, but on a macroscopic size scale. So on the size scale of humans, a flowing river, a bow and arrow. And I used a bow and arrow here because I said kinetic and potential energy. So this on a macroscopic scale. So this has potential energy when the of the string or elastic band here, and that gets converted into kinetic energy. But this is organized form on a human scale, size scale, macroscopic size scale. Okay, electric energy. You could say this is energy associated with electrostatic forces, but then when you say that there's the sense to include the electrostatic forces between electrons and protons, and that's more of associated with chemical bonds, chemical energy. So electrical energy is, as you know, is more referring to electrons, so electric current, static electricity, things like that, electrons. Most notably the organized form of kinetic and potential energy of electrons. So electric current or a voltage, which is a potential energy. You separate electrons. You have to pull them a force over a distance. You pull the electrons apart. There's no flow because you haven't completed the circuit. So there's a potential energy. You complete the circuit. You've got this current. Magnetic energy. So you have electric energy, and so with electric energy, you have electric fields, right? That's an electric field is representing the force that would be exerted on a charged particle if it goes into that electric field. Same idea with magnetic energy. You have magnetic fields, and it's similar in how if you have a current or a charged particle that goes into a magnetic field, there's forces that are exerted on it. Remember, magnetism and electricity or the forces between electrons, they're intimately related. Magnetism comes from flowing electrons. If you have electrons that are moving, they generate a magnetic field around them. That's what electric motors and generators operate off of, magnetic fields that are created by flowing current. Gravitational energy. So you've got electric fields, magnetic fields, and you have gravitational fields, right? We talked about if you have a body of water that's, kind of quote unquote been lifted up against gravity, then you're giving that, there's a force over a distance, that force against gravity, so you're giving it a gravitational potential energy. The roller coaster comes up here, and now it's not moving for a second, but it's got gravitational potential energy, and that gets converted to kinetic energy as it comes down. Chemical energy, so this is a form of potential energy. Remember, when you say potential energy, inherent to the definition of potential energy is the idea of the position of a mass. Well, based on the positions of these atoms and molecules, however you want to look at it, in relation to one another, in relation to the electrostatic forces between the protons and the electrons and whatnot, there's this stored kinetic energy within these bonds. And, just to point out, we talked about mechanical energy being kinetic and potential energy, the organized form on a human macroscopic size scale. But when you look at chemical energy in a microscopic sense, from things that take place in biology, in biological systems, in the human body, and for example, well, those are like, if you study microbiology and biochemistry. I mean, I'm not an expert. I've taken some biochem classes, and I've talked to chemists and biologists. Inside a cell, the mitochondria and all that, these are like micro machines. It's like real machines. And so from the perspective of the cell, the energy in these bonds is like a mechanical energy. Like ATP, that's like where the cells get energy. ATP will transfer a phosphate to it's called like a sodium potassium pump. That energy of that phosphate gets attached to the pump, and that pump changes configuration so it can push sodium against the grain, or potassium ions against the grain, and so it's like pumping. Well, right from that perspective, that's mechanical energy. Nuclear energy. So maybe you could consider this a form of chemical energy, but I think the name chemistry technically isn't associated with what's going on in the nucleus. Chemistry is like bonds between atoms with the nucleus staying intact. But this is just all of the stored kinetic and potential energy inside of the nucleus. In nuclear power plants, we take advantage of the unorganized form of this energy so that they heat from it. We can use nuclear energy, the heat that comes from it, to make steam, and steam turns turbines. Mechanical wave energy. So you want to put mechanical here because there's also electromagnetic waves, right? That's a little bit different. Mechanical wave is going through a medium, like sound goes through air or water wave. There's moving with a mechanical wave, there's moving mass. This is an organized form of energy, right? Radiation. So this is an electromagnetic wave. This doesn't propagate through a medium. This is an oscillating electric and magnetic field that comes from the movement of electrons, or any charged particle, like even like a electromagnetic waves, gamma rays coming from the nucleus is not it's not exactly electrons moving. It's like protons moving, accelerating fast. Surface energy. This is an important form of energy that people tend to forget about. It takes energy to create a surface. So all surfaces have energy. The surface of a liquid, the surface of a solid, not a gas though. There is no surface of a gas. Okay, and thermal energy. I put this last because if you go back through all of the energies we just talked about, all of them, there is some aspect of an organized form of energy. So even like nuclear energy, I mean, with that heat, you can push a piston. Same thing with chemical energy. But thermal energy is just a statement of the purely random motion of the molecules of a gas, liquid, or solid. Technically, it's just referring to the kinetic energy, the motion of a gas, liquid, or solid body, but you can kind of think of the idea of potential thermal energy as well.